Hello everyone, I'm Amir, and this is my topic, my research topic. So I did large language models versus graph neural networks for hierarchical reasoning on knowledge graphs. So first things first, in the real world, data is inherently nonlinear. Now, this is a cherry-picked example from the TensorFlow playground, but this is a very simplistic example of just what a neural network can solve, and they use that to demonstrate the concept of activation functions. But yeah, it's inherently nonlinear, and this is a manifold, uh, another nonlinear example. But nonlinearity can also be through graphs. In fact, both of those previous examples can be seen as a graph of nodes connecting to each other. Now, text is another example. Just graphs are all around us, like where uh, a sequence, a list can be seen as a graph, a tree can be seen as a graph, an image can be seen as a graph like this, or even like a molecule can be seen as a graph. But one type of graph in particular is the knowledge graph. And these knowledge graphs are supposed to represent basically relationships between entities. Uh, so one thing that has occurred recently is that I've been seeing a lot of tutorials, LangChain tutorials on LLM retrieval on knowledge graphs. And they've been shown to do reasoning on these knowledge graphs fairly decently. So let's try an experiment. Now, I have these two graphs on the left and the right. Uh, which one do you think is going to do retrieval on better is the question. So I also have it on here. Like this is Learn Anything, courtesy of them. But as it turns out, well, actually, I have a little chat window here. This is using OpenChat 3.5, but uh, and this is a mermaid diagram that I fed in as an input. I just fed it in a bunch of times, and there's like a lot of complexity. Then I asked it a question of just three random things that, based on three random things on this knowledge graph. I put marine ecosystem, Celtic, and behavioral studies. Just three random things, and it just came up with some random stuff. Uh, However, what it answered with is has nothing to do with actually all this. So here's what I want to demonstrate. The one that it actually does worse on is this one. It might seem like this one on the right is the worst one, but it's actually the one on the left. And uh, the thing is that the large models, as long as they can, they're large enough and have large enough context window, they're not going to struggle with something like the one on the right. Ignore the relationships because they don't matter on the one on the right. However, on the left, when there's a bunch of complex relationships, these LLMs they struggle. Now, the reason for this, why is this? It's because of hierarchy. And basically, when there's systems of hierarchies, uh, multiple systems of interdependent hierarchies within a knowledge graph, uh, the LLM, the large language model, can get confused. And this often happens, as uh, I'm sure many of you have seen with, like, for example, Perplexity.ai needs to start asking clarifying questions when you, for example, run into an error in your code and you need to solve it in some way. So I have a simplistic example of a knowledge graph on the right here, or on the top here. And I mean, an LLM can do stuff perfectly with this. However, once you get into the one on the bottom, which has tons and tons of relationships and tons of entities, there starts to become a problem where the LM literally has no idea what to do and it'll start hallucinating. Uh, the thing is that these language models have a weak representation of pragmatics. That's to say that, like, as you add more hierarchies and systems that are connected and interdependent on each other, like for example, one thing in the context of another thing, but or like let's say a cat is on a like a couch or something, but it's also in a suit, but he's getting chased by the CIA, or like as you start adding more stuff to the context, the LLM will get more confused. Well, to be fair though, that cat in the CIA example is like something the LLM wouldn't have a problem with, but you get the idea that as it goes to something like what is on the bottom, the LLM will have a problem with that, and it'll start spewing out hallucinations because it has a weak representation of pragmatics. And what I mean by this is that uh, essentially, as you keep adding more and more hierarchies to the context that depend on each other, the meaning of the context can change. For example, like the you could say something like "that's sick," and in the context of like "oh, that's sick, that's cool," uh, you're saying that to your friends. It means it's cool. But if you're saying "that's sick," in the context of like someone like killed someone and you're calling them sick in the head, well, that's not cool. Now that's a simplistic example that LLMs can totally get. But once you keep adding these hierarchies and get towards the bottom, the meaning of it doesn't know how the meaning will change. The meaning of the overall thing will change. And that's what I mean by pragmatics. Now, to dive deeper into this, uh, essentially, these state-of-the-art large language models, they struggle with these systems of hierarchies, and it's a symptom really of their training. The Many of these encoders and embedding models, they're trained using by predicting just mask training objectives with surrounding context uh, to then predict that mask training object or the masked word or token or whatever. But like I have on the right BERT here. However, that only takes into account the local hierarchy or the local context, you can say. Uh, it only takes into account what that surrounding context was while it was getting trained. So that's more so what it's like referring to, or it's more so relying on that. And in contrast, when there are multiple contexts interacting together in multiple scenarios, such that complex logic needs to occur in order to generate the desired output, which means the context is not local, the LLMs will hallucinate. And to remedy this local versus non-local context problem, well, I mean, even before that, I guess to expand on this training objective, there's also next sentence prediction, which similar issue. They basically the masked words and tokens, they don't fully capture the roles of interactions between the multiple information structures and hierarchies. So basically, it's great predicting the masked tokens or next sentence prediction. It's great for when the context of the input is local, which means that only the surrounding sentences need to be learned to infer the masked target. But when, for example, there's not just long range dependencies, but when these multiple information hierarchies are interacting with each other, like this, like the one on the bottom here, it's not going to learn that very well, and it will hallucinate. It will hallucinate. And to remedy this, the LLMs they try to compensate for this by uh, there's a few ways they try to compensate for this. So the main way that they're trying to compensate for this is that they try to train on these large, diverse data sets that incorporate these, or maybe before I do that, let me just give an example of something here, of this dependency issue I'm talking about in multiple, like interdependent hierarchies here. So I have some LARM text in this tokenization visualizer, and let's say somewhere in one of these sections, let's say this convolus token or something is the masked thing. This is the masked token, or this is two tokens, but just present as one. Uh, However, it the meaning of this, even though you have the context as this paragraph, the meaning of this is actually dependent on this, but in the context of this, but oh, there's a context of this, oh, but it's a subset of this, oh, but they're actually somewhat having this as a theme, oh, but this and that. Yeah, the LLM's not going to know. It's not going to be able to really capture that. So they try to compensate for this via these very large and diverse data sets that incorporate these kinds of uh, these kinds of relationships into the local context. And with this large and diverse data set, and to actually represent this diverse data set, the language models need to like they to match that, they need to have parameter count that can handle it. Hence the actual hence the birth of large language models. And the other thing is large context windows, which allows it so that it's not the local context, or I guess you can say, yeah, the local context from, let's say, an encoder uh, is now bigger. So it has more of a chance to uh, capture those dependencies and meanings. And then I would say the third thing is chain of thought reasoning. Now, this is a bit of a special case where uh, the skyrocketing parameter counts uh, to accommodate the large language models, or I mean, the local versus non-local context issue is also the reason that chain of thought prompting is successful. Because by allowing the LLM to have a chain of thought, it's able to somewhat circumvent this local versus non-local context issue by predicting what is essentially chained local contexts that autoregressively relocalize the relevant non-local context to bolster its final answer. Now, what do I mean by this? What I mean by this is that, let's say in this chain of thought example, you have Roger has 5 tennis balls, or I'm not going to read the whole thing, but essentially, uh, since it's doing that next token prediction, it's basically on the right track. So it doesn't need to, like, it's starting where it needs to be, or it's basically starting where the chain of thought should be. And as it predicts more token by token, it tends to predict the token that is the most likely next token happens to also be the token that is most likely to, in this sequence, eventually lead to the correct answer that is based on this global context, because now you're basically compressing your non-local context into a local context via this chain of thought. Hence the actual term chain of thought. Now, let's compare all this to graph neural networks. Graph neural networks, they're amazing. They There's so much I can say about this, but like essentially these latent representations from the LLM encoders, like just well embeddings, i.e. embeddings, they excel at capturing semantics, but they're weak in representing and capturing the complex pragmatics, as I've already demonstrated. That those complex dependencies of, let's say, a dynamical system is like, yeah, they're not going to capture that. For example, look at this Afghanistan stability dynamical system that I have on the right. An LLM is not really going to capture that entire thing. Well, it might, but let's just say it was a little bit bigger, and it probably wouldn't. But a GNN, by learning essentially the topology of the whole graph, the topology, the signal, the like, you can think of it as like uh, the silent promise, or the silent like unspoken rules. By learning those unspoken rules, i.e. the topology, it is essentially learning the pragmatics, because now it's able to learn why in many contexts, like in all these contexts, how something will behave, or how a node or edge or whatever it's predicting or is need to be predicted is going to behave. It learns a linear representation of a knowledge graph and thus better accounts for those pragmatics. And I've kind of already said this before, but the variable pragmatics are the effect of multiple interdependent hierarchies. Like, for example, let's say you had a friend group, and uh, let's say you had a friend group, the boys or something, and then a girl came into the friend group. That changes the whole dynamic. The boys aren't going to be talking as much about uh, boy things. The presence of the girl most likely will probably change the overall dynamic of the group. But now let's say you add in another person, and then another person, and then another person, and this group is expanding. And now, as the friend group gets bigger, it loses that homey feel. There might be a drama between them. Hell, it could even turn into a gang war if they get like big enough. Hopefully not. But what I'm trying to say is that these interdependent hierarchies will make the whole meaning of the system different, and it makes it very volatile. And the GNN is able to capture that. So for this comparison, now how are we going to compare this? Basically, I came up with three criteria. So given some complex graph, generate questions about the knowledge graph. And said questions must require hierarchical reasoning, as we previously defined, of knowledge of concepts in the knowledge graph in order to produce the right answer. Think of just like that CIA cat example. And if one answers those questions correctly, given the knowledge graph, we say they are performing hierarchical reasoning. So just to summarize, we're basically asking questions to to the model that require hierarchical reasoning of the knowledge graph. We're asking questions about the knowledge graph that to get the answer, it requires hierarchical reasoning. So these are questions, honestly, they could be like test questions, but that's what we can think. So we're going to do an experiment. And to limit our scope, we're doing multiple choice Q&A on the knowledge graph, and the hierarchical questions will come from Common Sense QA, and which is a data set, or which is it's a subset of Common Sense QA, the hierarchical ones. It's one of the most popular data sets for question answering, and I found it to be very, very useful. And ConceptNet will be the knowledge graph. It's a huge, huge data set of this knowledge graph. Like it's a huge knowledge graph. And I have Bicycle up here as one of them. And the LLMs that we're going to be testing is going to be Gemma, Mistral, Falcon, Llama 2, and the GNN will be QA GNN. And speaking of that, this is the architecture. It's essentially taking the knowledge graph, and it encodes using a language model actually. It encodes the question and uses the knowledge graph, and from there it basically goes through GNN layers to perform what is essentially reasoning, and then it pools through an MLP to create a probability score for each multiple choice question, and with those being A through E as options. And you see over here on the bottom diagram, it has this is just an example of how things go. So, and I actually trained one of these. It took 4.5 hours on my RTX 3080. You can see I did not write all the architecture. I did not actually come up with this architecture. Uh, Kudos to the person who did. It'll be in the references. But I had to essentially just retrain it because nothing would work on my system. So I just retrained it, and I had to, yeah. And you can kind of see what I have here. This is my notebook, and you can see the results here. So here are the results. I have it over here, the slides too. So unsurprisingly, this wasn't surprising at all. Basically, QA GNN, it ruled. It really ruled. Though what's fascinating though is the performance of the LLMs. Now, you would think that, gamma, instruct, and llama would do better than you would think at least gamma would do better than Mistral instruct. But unsurprising, or I mean, surprisingly, Mistral was the one who almost, or in some ways, got the closest to the QA GNN. And well, I guess you can say it's because the Mistral instruct seems to have the most instruction following behavior, just from my own experiments. Falcon is the oldest out of these, and then uh, the thing I found that I was found very fascinating and honestly kind of not surprising about Gamma and Llama is that they actually struggled with following the exact instructions unless few shot learning was applied or few shot prompting, which lend, lends further credence to the whole local versus non-local idea. So the conclusion is that state-of-the-art LLMs, they just struggle with capturing complex systems of hierarchies. And as a result, they weakly capture pragmatics. So they can't really reason hierarchically at a scale. However, GNNs do not have a problem with this because they learn the topology, they learn the unspoken rules of this system and society of the nodes and edges, and they're perfectly capable of reasoning hierarchically as a result. So, and we have shown this result to be the case experimentally. Thank you very much. Here are the references. Shout out to all y'all. And please support my future work. You can find stuff on my GitHub. Thank you.